Um, okay, now we're recording. Um, Singular value decomposition is an effective way to do um, effective way to do dimensionality reduction because it allows you to easily do principal component analysis. So to do singular value decomposition, you start by factoring the matrix into three components. And this generalizes diagonalization to non-square and singular matrices. So this is a visualization of SVD. Um, so what you're really doing is you're coming up with three components, U, sigma, and V. Sigma is effectively a variance covariance matrix. U stretches the data in the direction of greatest variance, and V is a reformulation of the data. I should stop right now. I realized I forgot to ask this at the beginning. MD, do you have any questions about the test or anything?
About the test, no, not really. So I had a question just about the today's topic. So about the dimensional reduction. So the first thing it says is reduce the data to its dimensions of the highest. When you say its dimension of highest, like what do you mean by that?
Highest variance.
Okay, so the variance of the data basically.
Yeah, you're finding the dimensions that effectively summarize the data. And by summarize, we're thinking about the ones where there's the greatest variance in the data.
Okay. And just to be clear, like I mean I try to understand like variance couple times, but could you explain like variance just a bit more for me?
Sure. So let me get out of here and just real quick go to OneNote. So the
I mean, I
idea of
kind of know the formula of it. Like I kind of know the formula of it. I was just like wondering like in terms of like when we look at the data, and like we're trying to find its variance, what exactly are we like looking for? Like
there are two primary so when we're talking about variance, we're making a statement about moments. So
hmm
you can think of the mean as the first moment. So
okay.
the mean is a measure of centrality.
Okay, yeah.
And then the variance is the second moment minus the square of the first moment. So what this effectively means is it's a measure of spread rather than centrality.
Okay.
Um, and so now if we have a variance, if we have a mean, that means that our PDF has an expectation that, let's say, it's somewhere around here. So that's what the mean means, is that there's an expectation, there's a central method measure, but the problem is the mean obscures a lot. So you could have this data set
hmm
and you could have this data set, and these data sets have effectively the same mean, but
Right.
they have wildly different variances.
Ah,
Put
okay.
another way, if we have two data sets, one of them looks like this, and let's say the mean is there, right?
hmm
The mean in X is there. Let's say the mean in Y is there. And then if we have another data set where it looks like, well, the mean in Y is there, and the mean in X is there. So if you're
Right.
just looking at means, these data sets look identical.
Mm-hmm.
But if you look at variance, now you've determined these data sets look very different.
Ah, okay. So that, okay, yeah, that makes more sense.
So variance is how spread out the data are.
So basically, when we're talking about dimensional reduction, we're basically trying to reduce the variance of the data.
Well, not exactly. What we're doing in dimensionality reduction is we have tons of we have a data set with tons of different variables, right?
Mm-hmm.
And so let me go back to OneNote for a sec here. We have a data set with tons of different variables. Let's say the data set looks like this. So you see there are all these columns, and each column is a variable, right?
Mm-hmm.
Well, we can't visualize as humans in more than 2 dimensions.
Right.
And we also can't real. So there's this idea in mathematics and statistics of the curse of dimensionality. And basically, the idea is in most statistical objects grow exponentially with the number of dimensions you have. So it gets harder and harder to analyze a data set the more variables you have.
Mm-hmm.
Think about running a linear regression and suddenly you have 1,000 variables.
Mm,
You
yeah.
can't do it, right?
Mm-hmm.
So dimensionality does, reduction does, is it says, well, actually, this isn't 1,000 variables because these are X variables and these are Y variables and these are Z variables. So it finds variables and it says, these variables are actually like these variables. And
Ah,
these
okay.
variables are actually like these variables. So you're saying,
Mm-hmm.
actually, I don't have 1,000 different dimensions. I have 3 different dimensions that are measured by 1,000 different variables. So basically, you have x1, x2, x3, x4,
Mm-hmm.
x5, and then you're saying I have variable y, which is a weighted sum of x1 and x2, and then my variable z, which is a weighted sum of x3 and x4. And actually, x5 doesn't contain a lot of information, so we're not going to worry about it. So you're putting
Ah, okay.
together a new data set that's made up of variables that are a combination of your original data set. But now, instead of having all these variables, you have a very small number of variables, and you're able to go from not being able to plot it or having to plot it in the nth dimension, which you can't do, to
Mm-hmm.
now being able to plot it in 2 dimensions where this is your y-axis, this is your z-axis. So these aren't real variables, they're variables you've created, but they're measuring things in your data. It's just that the original variables in your data didn't, there were too many to actually analyze each on its own, but now you can analyze combinations of them.
Right. Okay. Yeah, that makes much more sense.
That's a great question. I really appreciate it.
Yeah, of course.
So SVD is the kind of the first step in a common dimensionality reduction technique called principal component analysis. So the starting thing you do in SVD is you find the eigenvalues. So of A transpose. So this is your matrix A, and then you multiply it by its self transpose. Just to recall, A transpose will look like this: 3, 2, 2, 3, 2, -2. So we're flipping the matrix on its head, if it will. We're rotating it by 90 degrees. We're performing this rotation, and then we're multiplying the matrix. We're multiplying this by this, multiplying this by this. So this times this becomes this. 3 times 2, or so 3 times 3 plus 2 times 2 plus 2 times 2. And that equals 9 plus 8, which is 17. So that goes right there. And then 3 times 2 is 6, plus 2 times 3, which is 6, plus 2 times -2, which is -4. So that becomes 8. And then you have this times this, that gives you this. This times this, that gives you this. So you're multiplying A with A transpose. That's the first step of singular value decomposition. And then you find the characteristic equation. So this is how you find the eigenvalue. We'll go run through how you find the eigenvalue real quick. So find the eigenvalue, you do minus lambda here, minus lambda here, and then you take the determinant. The determinant of a 2 by 2 matrix, you do 17 minus lambda times 17 minus lambda minus 8 times 8. And then you solve that as a system of equations. I think I did that right, but we'll see on the next slide. So here we have, we multiplied all that together and we get this system of equations. Lambda squared plus minus 34 lambda plus 225. All right. And so now lambda minus, let's just get the solution here. Lambda minus 25 times lambda minus 9. So these are called your singular values. The roots of so the eigenvalue, which is the roots of the characteristic equations of A times A transpose, are the singular values. So you can think of the singular values as like a determinant of a non-square matrix. So A is a non-square matrix, so it doesn't necessarily have a determinant. But the cool thing about it doesn't have eigenvalues. You can think of them as eigenvalues of a non-square matrix. It doesn't have a determinant definitely, and it also doesn't necessarily have eigenvalues. Because it's a non-square matrix, it's considered singular and thus doesn't have eigenvalues. But we can take the singular values, which are very similar to eigenvalues of a non-square matrix. And here our singular values are 3, 5, and 0. 0 is always included in the singular values. So then we find the unit length kernel unit length vector in kernel of matrix A transpose A minus sigma squared I. So basically we subtract 25 times the identity matrix, which is sigma 1 squared from A transpose A, and then we row reduce it and find the unit length kernel. You don't really need to know what a unit length kernel is. You can look it up later if you're curious. But we do that for all 3 of the singular values. And then we get 2 vectors, and the final vector can either be done by doing this again, or by computing finding the unit length vector perpendicular to V1 with transpose perpendicular to V2. So that gives V3. And so now we have now we have sigma and V transpose. So sigma here is this matrix. Notice it's sigma 1, which is the first singular value, sigma 2, which is the second singular value, sigma 3, which is 0, which is the third singular value. And then this is the matrix we just found composed of those three vectors. And so to find u, you solve the equation sigma ui equals a vi for all elements of the matrix ui, and then that leaves you with this. So you multiply, or you can also do 1 over sigma a times vi will get you the same thing. So basically, you get this. You're never going to expect to do this on the test. It's just good to have seen it happen once to understand the steps. But basically, you get this, which is 3 matrices that, when multiplied together, get you back A. And so this is a process called singular value decomposition. And this is useful because it allows you to do something we're going to talk about in a moment called PCA without having to have a nice looking matrix. So principal component analysis is the most commonly used dimensionality reduction technique. It's used to reduce data to a combination of variables representing maximum variance, like we talked about before. So it has 4 steps. Standardize the data, compute the covariance matrix, SVD or eigen decomposition, and then select eigenvectors. So the first step is standardize the data. And so when we talk about standardize the data in this class, or really any statistics class, what we do is we take the original data, and for every variable, we take away the column mean. So if we have a data set that looks like this, we find the mean of this data set, mu1, mu2, mu3. We find the mean of each column, and then for each variable, x1 minus mu1, x2 minus mu, x11, x2, 1, 2, 2. So you just subtract the column mean from every object in the column for every data point, and then you divide. You have a column mean, and then you also have the column standard deviation: sigma 1, sigma 2, sigma 3, sigma 4. We were talking about variance before. This is the square root of the variance. So effectively, what you're doing, do you know, MD, what you're doing in when you're doing this? It's totally fine if you don't, but I'm curious, do you know what this process does, or what it really buys you?
When you say standard data,
When you're standardizing the data, what is this process buying you?
I'm not sure, to be honest.
So I'm making the mean equal to 0. And in theory, I'm making the standard deviation equal to 1.
Oh, so basically, normality of the data.
Exactly. I'm converting, if I assume my data is standard normal, is a standard
Distribution,
if
yeah,
I assume my data is normal random variable, it
right.
has this mean way out here and a standard deviation of who knows. And now every variable is going to have a mean of 0 and a standard deviation of 1.
Okay. So
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 this is
that's basically what they mean by standardizing the data. So all the
yeah,
variables have the same mean and standard deviation.
exactly. So we're transporting to a standard normal distribution, and this allows us to more easily compare all of the variables. So we've gone
Mm,
from a bunch of different variables with a bunch of different standard deviations and a bunch of different means to a bunch of different variables with the same variance and the same mean.
right. Yeah, that makes sense.
So now we compute the variance covariance matrix of the data. So effectively, for each row, so we have, for each column rather, we have call 1, call 2, call 3, call n. Effectively, what we're doing is creating a matrix that is the first element is the variance of call 1. So it's the variance of call 1, and then this element is the variance of call 2, and then dot, 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 variance of call n. So this is on the diagonal, which is right here, you have the variance of all of your variables. And then on the off diagonal, you have the covariance of all of your variables with each other. So basically, you're finding out how spread out each of your variables are. And this column should be something close to 1 because you've standardized the data. So this diagonal should be something close to 1. So what you're caring about is how related your variables are. So you know that your variables are generally pretty close to 1. But now you're wondering how related are my variables with each other. So really what you're measuring through this matrix is how alike the variables are. That's key to dimensionality reduction is you're trying to find out variables that are similar to each other so you can combine them to create dimensions. So now you select the top eigenvectors of the covariance matrix. So let's review. We standardize the data, we compute the covariance matrix, and now we perform eigen decomposition. We order so we're going to have a series of eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4, dot, dot, dot. And then we're going to have a series of eigenvectors that go with each of the eigenvalues. So we have a series of eigenvectors and eigenvalues, and then we select the top k eigenvalues and then the associated eigenvectors. So we order the eigenvectors by eigenvalues. We take the highest eigenvalues because they correspond to principal components, and they explain the most variance. Those are variables that are highly related to each other and that have explain a lot of the variance in the data set. And so if it's not, so can you do eigen decomposition on non-square matrix?
Uh, yeah, I'm pretty sure you can, right?
No.
No?
No, matrix has to be square to perform eigen decomposition.
Okay.
You have to be able to take the determinant.
Oh, right, of course, yeah.
So what can we do if we don't have a square matrix?
The transpose, like
We can
multiple the.
do SVD. So that's the
Right.
value of SVD is it allows us to perform PCA on a non-square matrix and allows us to perform eigen decomposition.
Oh, okay.
So the eigen decomposition gets you the most important factors and features of the data set. So here's PCA in a nutshell, represented visually.
I had a question actually. Yeah,
Sure.
just a few slides before. So when you said you get the top eigenvectors, when you said top eigenvectors, you mean like the highest values, like when you say
Yeah,
top.
the largest largest eigenvectors.
Mm-hmm.
So you order the eigenvectors by size, and then you pick the largest one.
So if it, like so the largest ones when we pick the largest ones, are we saying like they have like similarity in their data or like?
So yeah, so this lambda one, the eigenvector that is assigned to this eigenvalue is going to have some weights on data. So some of the data is going to be weighted higher,
Mm-hmm.
and then so it's going to have weights on the different columns, and then you're going to multiply the data by the set of eigenvectors. So you're going to combine the eigenvectors into one matrix, and then you're going to multiply it by a matrix called data. And then what you get out is your reduced form data. So what effectively happens is that individual each principal component, which is each eigenvector, is is a set of variables that represent a weighted set of variables that represents a portion of the data.
Mm-hmm.
So, have you ever heard of the Big Five personality test?
No, I don't think so.
Have you ever heard of anyone calling themselves like an introvert or an extrovert?
Yeah.
So, this is how they create that. So they have a test that gives out. They have a test that has a bunch of different questions. So you have a bunch of
Oh,
different
okay, okay.
questions,
I think I
and
know. I
then
think I know what you're talking about. Yeah.
yeah, each question represents a variable. But this is now a highly dimensional data set.
Right, right.
So what you do is you say this question and this question relate heavily to each other, and this question and this question relate heavily to each other. So we're going to call these two questions extroversion.
Ah, okay, okay. So that's basically they sort of reduce the dimension of the data to five variables, where like you have introvert,
Exactly.
extrovert, and like blah blah blah,
They
whatever.
found they found out that when we give these tests, what tends to happen is that these questions explain a lot of the variation in the data. And
Mm-hmm.
what they found out is that those questions tended to be able to be grouped in into these factors that we call parts of a personality.
Mm-hmm.
So think about when you're doing principal component analysis, think about it as you're figuring out the personality of your data set and the variables that are relating to certain factors.
Mm-hmm. Yeah, it makes sense because like it's somewhat similar to like the like some of the job postings, like if you apply to them, they usually give you like a test like pi metrics and whatnot. It's like somewhat similar to that.
Yeah. So principal component in a nutshell, you have correlated data and then you have high dimensional data. So you have a lot of dimensions of data. So you center the points. You compute the variance covariance matrix. You compute the eigenvectors and eigenvalues. You pick the highest eigenvectors, or you pick the eigenvectors based on the highest eigenvalues.
Mm-hmm.
You project the data onto those eigenvectors. And so that's what I was saying as you get your eigenvectors into a matrix and then you multiply it by your data. And so that gives you the reduced form data.
So that's basically what you essentially mean when you say project the data into the eigenvectors.
Correct.
Okay.
And then now you have uncorrelated low dimensional data. So to give you kind of a visualization as to what this looks like, you start off with a bunch of different variables, and then you go to two variables that represent two different dimensions. And so these dimensions explain a lot of the variance in the data. And so you're spreading them, adding the data out based on the variables that represents the greatest variance. So this allows you to say, well, these data points are like each other. These data points are very different. So that's a big use of principal component analysis, is it allows you to say, find features in your data set and allows you to say, what is similar about these data points? So while I was working at the Federal Energy Regulatory Commission, one of the things they wanted me to do was to take, so one of the things I did was I did principal component analysis on this big data set they had, and then I plotted the data, and I said, well, these generators don't look like these other generators. These generators are outlying points. And so then I said, well, if these generators are outlying points, what are they doing that's making them so different? And so that was a way of anomaly detection. So this allows you to group your data and find out if there might be anomalies or what features might be interesting in your data. So PCA is an unsupervised algorithm, but there's another algorithm called LDA, or linear discriminant analysis. PCA attempts to find principal components that maximize variation, while LDA finds variables that maximize separability between groups. LDA is common in topic modeling. So to give you a visualization of how LDA works, you're basically telling it that you'd like it to find variables that separate the different topics. And then it finds the variables that push the data furthest apart. So that's LDA. You don't need to know too much about it, but just know that it's an alternative to PCA with supervised data. So PCA allows you to look at your data, and you don't necessarily need to know anything about your data. You can just like figure out like what goes together, and this is a great way to explore your data. LDA is, I know that my data has these features. How do I separate it by those features?
Okay.
So now we're going to talk about something that's a little bit different, which is the bias variance trade-off. It's the mean squared error, which is a pretty common metric throughout all of machine learning, and it's actually the main metric we use in econometrics. The mean squared error is sum of 1 over n times x minus x. Let me go back. 1 over n sum y minus y hat squared. And so that's actually, the linear regression is designed to minimize least squared error analytically. That's what we're trying to do, least squares linear regression. So we have this idea of a bias variance trade-off in statistics. So the mean squared error is the bias squared plus the variance plus the baseline error squared. So there's a minimum level of error, and you can find that you can find that right here. And you minimize the level of error by minimizing the bias squared plus the variance. So you can think of the bias as how wrong you expect to be. And you can think of the variance as how precise you are. So there's this handy little graphic I like to show. This is low bias and low variance. You're always hitting the target. This is high variance and low bias. You're always getting kind of near the target, but you're like kind of all over the place around the target. This is high bias, low variance. So you're really precise. You're always hitting the same spot, but you're never right on target. And this is high variance, high bias, where you're really wrong and you're also all spread out. So what you really want is low variance, low bias. But there's a trade-off because the higher the bias is, generally the lower the variance is, and the lower the variance is, or so the lower the bias is, the higher the variance is. So there's always a happy medium. So a good way to think about this is that a really biased but low variance estimator would be the mean. It's always going to be a little bit off, but it's on average going to do well. A low bias, high variance, a low variant, a low, a high variance, low bias estimator is basically a model that is tracking the data really well. So what this is basically saying is there's an optimal amount of model complexity. So you don't want to just take the mean, because that's a really dumb model and it's really not getting you much. And you don't want to perfectly track the data, because that's also not getting you much. That's going to have way bigger errors as well. So you have these ideas of overfitting, underfitting, and good balance. So is this a really complex model or a really simple model, this overfitting one?
Overfitting, I would say it's a complex model.
Yeah, it's a complex model. There's a lot that goes into it, and it's really just tracking the data. What about underfitting? Is it complex or a simple model?
Um, I guess the opposite would be it's a simple model.
Yeah, but we've just taken the mean. That's all we've done. So there's high bias, but there's very low variance.
Mm,
So we're always going to be about accurate, but we're never going to be all that accurate.
right.
All right, and then here, low bias, low variance, we have a relatively simple model. It's not the most simple model because we haven't just taken the mean, but we also aren't just tracking all data points. So you don't want to, when you're doing this, you don't want to create the most complex model possible. You want to create a model that's the right amount of complexity for your problem. And a way you deal with this in practice is you split the data into 2 or 3 data sets: training, testing, and cross-validation. So data are split to make sure models fit out of sample data correctly. Cross-validation data set is used for parameters. Basically, what I'm saying there is you use the training data to learn about your model and figure out how to learn about your data and figure out how to get the model correct. Use the testing data to figure out how well your model works and whether or not you have a good model. So you're leaving out a little bit of data so that you can know things about your data. So you can know how well it works. And so why do you think you might leave out a little bit of data?
So, okay, just to get it straight, so the training data is just purely for training, and then the te what testing data is to see, like, once you have trained your model with the training data to see how your model performs using the testing data,
Right.
and then the cross validation data is just the amount of data that you sort of leave out, right?
So the cross-validation data is basically data you use to train your parameters. So
Parameters. Okay, okay.
I have a model that I've chosen based on my testing data.
Mm-hmm.
So F of alpha, beta, gamma. But there are a bunch of parameters in here I can do. So I'm going to train it on the trained data, and then I'm going to try all the different parameters on the testing, on the cross validation data. And then I'm going to choose my parameters, and then I'm going to test it on the testing data.
Okay, okay.
So you leave out testing data because you don't want a model that's perfectly fit to the training data and then doesn't work on the testing data.
Ah, okay.
So you leave out testing data so that you don't overfit. So there's this old joke in computer science that, let's say you're going to a conference and you're a discussant at the conference, but you fall asleep in the middle of the. So discussants have to ask questions to the people who are giving presentations. You fall asleep in the middle of the talk. You fall asleep. It's been a busy night. You had to travel here. And then suddenly you wake up and everyone's looking at you and you have to ask a question. You're like, oh my God, what am I going to ask? And then you think, I got it. How did you tune K? And the joke here is that in every model, there's always going to be a variable called K. And let's say the presenter in that discussion, you've forgotten by the end of this talk what it was about. It was a long talk. It was very boring. You didn't write the data portion of it. Well, you don't know how you tune K. Well, there's always an answer you can give, and it's cross validation. So there's always going to be a variable called K, and you'll always find it via cross validation. Cross validation allows you to choose model parameters by testing the model on data other than the test set with a wide range of parameters. So what you're going to do with the cross validation is you're basically going to say, well, we have an alpha. What if alpha equals 0.01? What if alpha equals 0.02? What if alpha equals 0.03? What if alpha equals 0.04? Turns out that works best when alpha equals 0.02. So we're going to use alpha equals 0.02 as our model alpha, and then we're going to test with alpha equals 0.02. So you can use a separate data set, or you can also sometimes split the training data set. So sometimes you don't want to leave out data for cross-validation because you don't have a lot of data. So what you do is you use something called k-fold cross-validation. And here you divide the data into k-folds. So you randomly split the data, you randomly sample the data until you have k different parts of the training set. And then for each part of the training data set, you train the parameter with parameter on k minus 1, and you do this for every different possible value of the parameter, and you test for the parameter on the last data. You repeat this for every part of the data, and you take the average error, and then you use the parameter with minimal error, and then you run that on the test set, and that's your parameter. So k-fold cross-validation is basically you split up your data randomly, and then you figure out what values of parameters work on the portion of the data are seeing. Another common way to do this is called leave one out cross-validation. And basically, instead of dividing into portions, you leave one data point out and you test on the you train on the rest of the data in the training set, and you test on that data set for the parameters. this is computationally expensive, but if you don't have a lot of observations, you don't want to lose anything to cross-validation, this can be a really good way to do it. Another way to do it is stratified k-fold cross-validation. This is commonly used for classification tasks, and it basically makes sure that you match the proportions of observation in the training data in your cross-validation samples, because you don't want to have it end up so that you have a cross-validation sample where all the red ends up in one and all the blue ends up in another. You need the groups to be equal across the different strata. So that is our presentation for this week on dimensionality reduction and cross-validation. And now I'm going to real quick run through some code on these two techniques. So let me start off by talking about how the code works more broadly, and then I'll run as much of it as works. I'm not sure that this code is working, but we'll hope it works. So I have an example matrix. I create my matrix. I compute singular value decomposition. So and then I perform PCA. So this is an example principal component decomposition. Or sorry, this is an example singular value decomposition. This is an example singular value decomposition. This is an example principal component analysis. I have my matrix. I standardize the data. I compute the variance covariance matrix. So compute the variance matrix of the centered data. I perform eigen decomposition. So I find the eigenvalues and eigenvectors of the data. I take the top k eigenvectors. I project the data by taking the dot product of the centered data and the principal components, and then I visualize the results. So here I'm taking the top two principal components, and then I'm plotting them. So let's see if I wrote this code correctly. So it's importing the packages right now. So this is the principal component plotting. So notice that there's more variation in the blue or the purple. So this is the original data, and this is the projected data. So the original data has a lot of variance. It's really spread out, and the projected data is really centered, and it's clearer how the data varies across the two principal components, which is it varies a lot across principal component 1 and not that much across principal component 2. And probably these data points are much more like each other. These data points may be outliers. And so this is now our reduced form data set. So that's principal component analysis. And then now let's talk about LDA. And notice right here, just to remind you, we're doing this. So here we did this from scratch. We just calculated principal component analysis from scratch. We can also do principal analysis with sklearn. So sklearn will do it automatically for us. And let's try now. Actually, I'm not going to do it. But yeah, that's principal component analysis. You just do PCA equals PCA, number of components equals 1. And then x reduced equals PCA, that fit transform x. And now let's try to do two principal components. Did that work? So let's try to do two principal components. That was just one principal component. Let's try to do two. Oh, let me plot them. Never mind. We won't do that. We won't. But yeah, you can change the number of principal components, and then you can plot them against each other. And so now we are going to do LDA with sklearn. So LDA, we have this data set that's a matrix of ones and zeros. So it's a vector of ones and zeros. It's labeled data. So now we perform LDA with X. So we have our X here. Earlier we didn't have labels. Now we have labels. We add labels, and then we perform linear discriminant analysis where we separate out the data based on our labels. And there we have it. We have the dimensions that separate the data based on the greatest variance. So review what we've done. First off, we performed singular value decomposition using NumPy. So we got V transpose, and U, or V transpose, sigma, and U. So we did singular value decomposition in case you ever need to do it. Then we performed PCA with NumPy. Then we performed PCA with sklearn. Then we performed LDA with sklearn. Another thing that you're not going to need to know, but you can do at some point, so you can look into it if you're interested. You can also do TSNE, which is another technique for dimensionality reduction called T-distributed stochastic near-neighbor embedding. And this also will reduce dimensions. And that code was the one I was worried about. That code's not working right now. So we'll go on to the next one. And I'll load in the packages while I'm running through discussing the code. So first off, we're going to load some data. This is called the iris data. It's a famous data set about flowers and data science. So it's a data set a lot of people will have heard about, and you'll work, pretty much everyone who's taken a data science class at some point has worked with the iris data set. And
Yeah,
then
we worked with this data set in R, like during the R laboratory.
Where was the IR laboratory with?
So it was an AMS course that I took. It's like AMS 394, and we just worked with worked with the iris data set there as well.
Cool, that's great. So we have X, which is our data, and Y, which is our target. And we split the data into train and test for X, and then train and test for Y. We give it the size of the split and a random state because we want to get the same results every time. And then we perform k-fold cross-validation. K-fold is coming from sklearn model selection. And then, so we're initializing k-fold so that we can perform it. And then we're running a logistic regression on the iris data. Then we're performing k-fold cross-validation. We're printing the results and the average accuracy. Then we're doing the same for leave one and stratified k-fold cross-validation. So let's see how this works. So average accuracy, 97%. Very simple data set. Logistic regression is a great model with k-fold cross-validation. And then we perform leave one out cross-validation, again with sklearn. And again, 97%, simple data set, simple model. And then we do the same with stratified, and we get the same results, but you can get very different results depending on how complex your data set is. I'm sharing a screen right now, right?
Yeah, I can see it.
Cool. So that's really all I had planned for today. Any questions?
No, about the no, not really as of right now, no. But I had a question like sort of not relating to this, like to the course as of now.
Okay.
I was just wondering, so I'm sort of like planning to do some projects with like data science and like sort of predictive modeling. So I was wondering if you have like any ideas regarding like what projects I can do or like what sort of data sets I can work with.
So I think this is great you're doing this. Employers love seeing projects on your resume,
Mm-hmm.
and employers love seeing people who add things to GitHub. So I think that's great. I think the first thing I'd say is I'd really caution against using data sets you've seen other people use before. So something
Okay.
like the Iris data set, if you talk about that in an interview, if you put that on GitHub, that's going to that's not going to really impress people.
Mm-hmm.
Um, you know what? We have extra time today. So you know what? Screw this. I'd planned on doing this in the last week,
Right.
but it's actually really valuable to get this done early. So let me walk through some of the data sets that you have access to that are really useful.
I was going through like some data sets on Kaggle to like look through so yeah, I was just wondering like what's type of like there are different types like financial data sets or like if they're trying to project the housing market data set or like
So I
health
would
data
avoid
sets.
Kaggle.
Huh?
I would avoid Kaggle.
Really?
Yeah, Kaggle is clean data that's not like what you see in the real world.
Ah,
And
okay.
also, it's employers here you've done Kaggle and they hear that you're basically a regression jockey. So that's not
Mm,
where economists thrive. Economists thrive with high context on data sets.
mm-hmm,
So these are a bunch of different data sets.
mm-hmm.
And I'd encourage you to, when you do a project, look into the data set and start thinking about a question you're really interested in. Fred has really great macroeconomics data.
Mm-hmm.
If you're interested in housing, I would also recommend looking at either the Federal Home Loan Bank data
Mm-hmm.
or the Consumer Financial Protection Bureau data. The Economic Research Service has really great data on agricultural economics. I used to work there, and they have some really great data on agriculture and agricultural economics, particularly
Mm-hmm.
if you're interested in food insecurity. Energy Information Administration. Energy is a place with big data. If you're interested in renewables,
Right.
EIA is a great place. NAS is again an agricultural statistics agency, and they have some really good data. Census has great data, particularly if you're interested in geographic data.
Right.
OECD has some good international data. IEA has energy data. BEA, BLS, BEA has good macro data. BLS and IRS have good data if you're looking for micro data, if you're interested in survey data. But
Mm,
if you're interested in financial data, I'd really encourage you to look into WRDS.
WRDES. Okay.
WRDS, you need to reach out to the school to get approved to access it.
Mm-hmm.
But we're approved to access it as Stony Brook students. And if you reach out to the school, other options. If you reach out to the school, you can get access to WRDS, which is really the gold standard of financial data. So you get some really great financial data here. And
Um,
if you ever want to, during office hours, we can just sit and like go through data, and we can, if you'd like to, we can talk through and work out a project. Employers don't want to see that you can like run a model.
right.
Employers want to
Yeah.
see you can take a project start to finish, and you can come with an interesting research question that you care about and work it all through.
That's interesting. Like, yeah, that's really interesting that you mentioned about about Kaggle because I did notice it too. Like most of the time, they usually just clean data set, and most of the time you're just sort of, uh, just building model just on a performing and like exploratory data analysis on a clean data set. I didn't think about it. Like now that you mentioned, like most of the times you won't really have sort of clean data sets ready for you to like like do whatever you want. You sort of have to navigate through the data set and sort of understand what you want to do and like what you want to find out about the data.
Exactly. You're never going to beat the best people on Kaggle because the best people are spending all this time. They have access to great computers. You don't want to beat the best people because it's not interesting. But as an economist, what you can do is you can build really interesting models to answer interesting research questions.
Mm-hmm.
So this is CombiStat. It's something we have access to that has a lot of financial data. We also have access to something called CRSP, which is stock data and price data. If you're really interested in financial data, or you can also look into Yahoo Finance, figure out yourself. But we
Mm-hmm.
have some really great data as Stony Brook to WRDS that I think there's a lot of questions you can answer it with. If you ever want
Mm-hmm.
to meet up during office hours or after this course ends, like we can talk through questions you could ask and how to build up a model. Because employers don't want to hear, I built these models. They want to hear, I did this interesting thing and I answered this interesting question.
Yeah, for sure. Yeah.
These are
I'll
also some
definitely look that. Yeah.
common economic surveys if you're interested in survey data.
Mm-hmm.
So yeah, those are some data sets that are very good. Yeah, the being able to come up with a question, ask a question, then answer it using data is an incredibly valuable skill set to have as an economist.
Mm-hmm. For sure. Yeah. I'll definitely look into like the different data sets like the different sources you gave and like look for some data to work with and sort of slowly work my way.
Great. Happy to talk about this anytime.
Yeah, for sure. For sure. Thank you. I appreciate it.
All right. I hope you have a great day.
Yeah, you too. Bye bye.